716 times every single second. That is how fast the fastest known pulsar star spins. A dead star the width of Manhattan, whipping around so fast that the surface is moving at 1/4 the speed of light. It has never been caught glitching, but a slower pulsar did glitch, violently. And that single failure cracked open a 50-year argument between 3 groups of scientists who still cannot agree on what went wrong. The Crust camp says the outer shell fractured under impossible pressure. The Superfluid camp says a frictionless liquid inside the core dumped its stored spin in one lurch. A third group says both teams are working with the wrong blueprint entirely. The failure happened to a pulsar called Vela, roughly 800 light-years from Earth, spinning at about 11 times per second. In 1969, astronomers at the University of Sydney were tracking its rotation with radio telescopes, logging every pulse, building a slowdown curve that matched the predictions almost perfectly. Pulsars are supposed to decelerate. They bleed rotational energy into radiation. The spin drops by a tiny fraction each year, and the timing data traces a smooth descending line. Vela had been following that line without a single notable deviation for as long as anyone had been watching. Then the line broke. On one recorded day, with no solar flare, no gravitational disturbance, no change in the surrounding environment that any instrument picked up, the spin rate jumped forward. The star accelerated. In absolute terms, the change was a fraction of a rotation per second. In the context of a timing system accurate to 14 decimal places, the jump registered like a crack in a load-bearing wall. Something inside the star had fed energy back into the rotation, and nobody could explain where that energy came from. This was not a measurement error. When the team rechecked the data, the jump was clean. It was not gradual. The spin rate had been on its predicted curve at one measurement and off the curve at the next. Whatever happened inside the star had happened fast, between one pulse and the next, in a window smaller than a fraction of a second. The star had been losing energy for years in a steady, predictable drain, and then, in an instant, some mechanism had reversed the flow and pushed energy back in. That question has now been open for over 50 years, and the 3 camps fighting over it are further apart today than they were in 1970. To understand how something this massive breaks, you need one piece of the timeline. The first pulsar was detected in 1967 by a graduate student at Cambridge named Jocelyn Bell. The signal arrived every 1.337 seconds, so regular that her team labeled it LGM-1 for Little Green Men, because they briefly considered the possibility that an alien civilization was transmitting. It was not a signal from anyone. It was the first neutron star caught spinning in the dark, sweeping a beam of radiation past Earth like a lighthouse on a coast nobody knew was there. Bell's discovery earned a Nobel Prize, though the award went to her supervisor, not to her. That controversy still has not been settled. But the question this investigation answers is not how pulsars were found. The question is what went wrong inside one. A neutron star is what remains after a star at least 8 times heavier than our Sun exhausts its fuel and the core collapses. The collapse takes less than a single second. An iron core the size of Earth compresses into a sphere roughly 20 kilometers across, containing more mass than our entire Sun. A teaspoon of the material would weigh about as much as Mount Everest. The gravity at the surface is 200 billion times what you feel sitting in your chair. A marble dropped from 1 meter above the surface would strike at roughly 7 million kilometers per hour. For comparison, the fastest bullet ever fired travels about 1.7 kilometers per second. The marble falling through 1 meter of a neutron star's gravity field would be moving at nearly 2,000 kilometers per second when it hit. The outer layer is a solid crust of iron, 1 to 2 kilometers thick, harder than anything that exists on Earth. Below that crust, the density keeps climbing into territory no laboratory and no particle accelerator has ever reproduced. What sits at the very center is genuinely unknown. Some physicists think it might be quarks that have separated from their usual confinement. Others think it could be an entirely new phase of matter that nobody has correctly described. The honest answer is that the deepest interior of a neutron star is one of the last places in the universe where the physics is still a blank page. Here is what happens in the dark. When one of these objects spins, its magnetic field fires a beam of radiation from each magnetic pole. Those poles are tilted off the spin axis, so the beam sweeps circles through space on every rotation. If a beam crosses Earth, all of us pick up a repeating tick. So what is a pulsar? A spinning neutron star whose beam happens to point our way. That is the full definition. Not every neutron star qualifies. The beam has to cross our line of sight. There could be millions of them spinning in the dark right now, invisible to every telescope, their beams sweeping through empty space and hitting nothing. Some neutron stars have magnetic fields so extreme that they get classified separately as magnetars. But the objects at the center of this investigation are defined by their spin, not their field strength. The fastest spinning star on record, PSRJ 1748-2446 AD, completes 716 full rotations per second. In mechanical terms, that translates to 42,420 RPM. Most car engines redline somewhere below 7,000. A Formula One engine at maximum output reaches about 15,000. This dead star is running at nearly 3 times that without interruption and has been doing it for millions of years. The only thing preventing it from shaking itself apart is the gravity, pressing inward from every direction at once with a force 200 billion times stronger than what keeps you in your seat. And because these pulses are so regular, millisecond pulsars keep time so precisely that some of them rival the best atomic clocks ever built. The pulsar sound that gets passed around online, that rhythmic ticking or droning hum, is not actual audio from space. It is a radio signal converted to a frequency human ears can register. Each tick is one full rotation. At 716 ticks per second, the sound flattens into a single sustained note. Back to the failure. Vela glitched in 1969, and then it glitched again in 1971 and again in 1974. Not at regular intervals, not with any predictable pattern anyone could map to an external cause. Each time the spin jumped, held its new rate for a period that varied from event to event, and then resumed the normal slowdown, as if nothing had happened. The star gave no warning before a glitch and no obvious aftershock once it settled. Astronomers named these events glitches, borrowing a word from electrical engineering for a sudden malfunction in a system that otherwise runs clean. The Vela pulsar became the most closely watched rotation anomaly in the sky, and every new glitch deepened the argument about what was happening inside. The Crust camp built the first reconstruction. For anyone who has watched a concrete dam develop a hairline fracture under decades of water pressure, the logic lands immediately. As a neutron star decelerates, the interior adjusts its shape, wanting to pull back into a tighter sphere as the outward spinning force dies down. But the outer crust is rigid. It hardened at the old geometry and physically cannot follow the interior's adjustment. Strain builds up invisibly through miles of frozen, compressed iron, year after year, sometimes decade after decade. No external signal, no warning pulse. The iron just absorbs more and more stress invisibly until it crosses the breaking threshold. Then the crust fractures and the star's shape shifts in a fraction of a second. Stored mechanical energy floods back into the rotation and the pulsar lurches forward in one sharp jump. Astronomers called the event a Starquake, borrowing the term directly from seismology, and the comparison was not just poetic. The physics of the failure is fundamentally the same as an earthquake, just happening inside a material a billion times denser than rock. on an object where the surface gravity would flatten a battleship into a film of atoms. For the smaller glitches, the Starquake model worked cleanly. Sharp events with fast recoveries where the crust cracked and the star quickly settled into its new configuration. The papers were published, the conferences moved on, and the Crust camp had the field more or less to themselves for nearly a decade. But the later Vela glitches blew that confidence apart. The spin-up carried more energy than 2 kilometers of crystalline iron could physically store, no matter how much strain had accumulated. The shell was too thin and too brittle to contain the answer. Something deeper had to be involved, and the Crust camp did not have a mechanism for it. The Superfluid camp built directly on that failure. Below the rigid crust, they argued, the neutron fluid drops into a state that has absolutely zero friction. A superfluid. In this state, the interior can rotate at a completely different speed from the outer shell. Picture a sealed steel drum filled with motor oil. Spin that drum to the red line, then hit the brakes hard. The steel casing stops, but the oil inside keeps swirling. Now replace the oil with a liquid that has absolutely zero friction. It never slows down on its own. It just keeps spinning at whatever rate it was moving when the crust last gripped it. While the crust decelerates over months and years, the superfluid maintains its old speed. 2 parts of the same object, rotating at different rates, building up a speed difference that grows larger with every passing month. When the difference becomes too large, the superfluid releases its excess rotation into the crust in one transfer, and the star speeds up. They looked at the same glitch and came to the opposite conclusion. The Crust camp said the shell cracked under accumulated strain. The Superfluid camp said the shell got pushed from below when the frictionless interior finally let go. Same glitch. 2 completely opposite stories, like 2 mechanics staring at the same blown engine and blaming different parts. Based on what you have heard so far, which explanation would you bet on? Leave your pick in the comments before the 2016 data changes the picture. And the superfluid version could handle the big glitches, the ones where the energy was 10 or 100 times more than the crust alone could store. A frictionless ocean of nuclear material, spinning independently for years or decades, carries vastly more rotational energy than a thin, brittle shell. But the superfluid model had its own fractures that the Crust camp hammered on relentlessly. Not every glitch recovered the same way. Some showed a fast partial snapback, as if the crust absorbed the transferred energy and then bounced part of it back, the way a shock absorber recoils after a hard compression. Others showed almost no recovery at all, as if the energy transfer was permanent and the crust simply accepted the new spin rate without pushback. The aftermath signatures varied wildly from one glitch to the next, even within the same pulsar. If the mechanism were a single clean transfer from one component to another, the recoveries should have followed a recognizable pattern, the way an engine returns to idle in a predictable sequence after a rev spike. They did not. Every glitch had its own recovery fingerprint, and the superfluid model had no explanation for why the fingerprints kept changing. For decades, the argument sat in that position. 2 models, 2 subsets of glitches each one could explain, and a growing stack of events in between that neither could fully reconstruct. Conferences turned into the same debate on repeat. The same data sets, the same counter-arguments, the same unresolved middle ground. Then in 2016, a team of radio astronomers in Australia decided to force a resolution. They pointed the Mount Pleasant telescope at Vela and kept it locked there, sampling the spin rate not once a day or once an hour, but dozens of times every second. Previous glitch measurements had always been reconstructed after the fact, comparing the pulse timing from before the event to the timing after. The detail of what actually happened during the spin-up, the internal mechanics of the transition itself, had always been lost in the gaps between measurements. This campaign was designed to close that gap entirely. The telescope watched Vela around the clock for months, logging every single rotation. waiting for the next glitch the way a seismometer waits for the next earthquake. The team knew it would come. They did not know when. They did not know what the high-resolution data would show when it did. When the glitch arrived, the data showed something neither camp had predicted. The spin-up was not one clean jump. It happened in distinct stages. A fast initial spike, sharp and immediate, consistent with something fracturing or releasing in the first microseconds. Then a secondary rise on a longer timescale, seconds rather than microseconds, as if a completely different mechanism engaged after the first one finished. The two events overlapped, but they were clearly separate processes operating on separate timescales. The recovery was equally layered, with different parts of the star adjusting at different speeds over different time frames, some snapping back quickly, others dragging out over days. The Crust team easily explained the first microsecond of the spike, but their models fell completely silent on the second wave. The Superfluid group had the math to account for the massive energy surge, but absolutely no idea why it stuttered. The data from that single event broke both reconstructions at the same time. That result blew the argument wide open. The interior of a neutron star, a third group argued, is not a two-layer system with a rigid shell sitting on a frictionless ocean. It is a multi-phase structure where the crust, the superfluid neutrons, the superfluid protons, and possibly exotic states of matter, deeper in layers of frictionless fluids and heavily compressed material, constantly grinding against each other in ways that no current model fully captures. For years, everybody treated the star like a shell wrapped around a core, a two-layer picture simple enough to build a model on. But the second the Mount Pleasant telescope delivered split-second high-resolution timing data, the old picture ripped in half. The staged spin-up, the layered recovery, the multiple timescales operating simultaneously inside a single event, none of that fits into a picture where only two components are talking to each other. There had to be more layers involved, more coupling points, more physics that the original framing was never designed to contain. The 2016 Vela glitch was not one team getting the mechanism wrong. It was the entire conceptual framework hitting its limit. So, who is right? All three teams are staring at the wreckage of the same machine, and none of the blueprints match. The Crust camp handles small, clean events. The Superfluid camp handles the biggest energy dumps. Neither can explain the staged behavior from 2016 without borrowing from the other side. And the third camp has correctly identified the gaps, but has not delivered a unified replacement that predicts the next glitch before it happens. Nobody has closed this case, not even close. What caused the rupture inside Vela? Drop your answer in the comments. Crust fracture, superfluid slip, or something that has not been named yet. We want it on record. At this point, it stops being astronomy and starts looking like a failure analysis. The interior of a neutron star is the densest stable material in the known universe. One step denser, and you cross into a black hole. If you compressed every human being alive, all 8 billion standing shoulder to shoulder, and then crushed that mass down to the density of an atomic nucleus, the result would fit inside a sugar cube. A neutron star takes that density and multiplies it several more times across a sphere 20 kilometers wide. That is not a number anyone built a machine to study. The Large Hadron Collider, the most powerful particle accelerator ever constructed, slams protons together at velocities approaching the speed of light, and the conditions it produces are still orders of magnitude below what exists 2 kilometers beneath the surface of a quiet neutron star. There is no way to recreate this material on Earth. The only way to study it is to watch what the star does when something breaks and work backward from the wreckage. Every pulsar glitch is an involuntary seismic reading from an object nobody can cut open. There is a direct technology consequence. Millisecond pulsars are currently used in networks called pulsar timing arrays, which detect gravitational waves by tracking pulse arrival times from dozens of stable pulsars spread across the sky. When a gravitational wave passes through the galaxy, it shifts those arrival times by billionths of a second. The system only works if the pulsars are predictable. Every unexplained glitch introduces noise into the instrument. If glitches stay unpredictable, the most sensitive gravitational wave detector in existence loses resolution at exactly the frequencies where the signals are weakest. There is one reason this matters down here. When two neutron stars spiral into each other and merge, the explosion forges every element heavier than iron. Every heavy element in your phone, in a reactor, or in the ring on your finger was likely created in exactly that kind of event, billions of years ago, scattered into the cloud that became our solar system. This channel has already covered that process in detail. In February of 2026, a research team using the Green Bank Telescope in West Virginia announced a candidate millisecond pulsar near the center of the Milky Way, close to the supermassive black hole Sagittarius A star. The region around that black hole is one of the most violent neighborhoods in the galaxy. Stars orbit at thousands of kilometers per second. Gas clouds spiral in at extreme temperatures. Radiation floods every frequency band. Finding a pulsar signal in that noise is like picking out a single ticking watch in the middle of a building collapse. The candidate is designated BLPSR for Breakthrough Listen Pulsar. If confirmed, it would be the first pulsar ever found in the most extreme gravitational environment in our galaxy. A clock ticking next to the strongest gravitational drain we can observe. The timing distortions from the black hole would test general relativity at a precision no previous measurement has reached. Interesting signal, not confirmed yet. If that pulsar is real and it glitches while sitting in the gravitational field of a supermassive black hole, the data becomes a reconstruction problem none of the three camps can currently solve. A sudden spin-up in normal space is hard enough to explain. A sudden spin-up, where time itself runs at a different rate depending on distance from the black hole, adds a dimension the existing models were never designed to handle. If you had to bet on one explanation for pulsar glitches and commit before the next Vela event, which camp gets your money? Drop it in the comments. We want it on record before the data comes in. The investigation stays open. A dead star the size of a city, spinning fast enough that its surface outruns most things in the observable universe, suddenly speeds up for reasons 3 teams of scientists cannot agree on and cannot reproduce in any laboratory. One side insists the rigid surface cracked under unimaginable strain. The other is certain the liquid core surged without warning. The 2016 data says both stories have gaps large enough to lose a theory in. And somewhere inside that 20-kilometer sphere of the densest material that exists before physics gives way entirely, the answer is sitting in a layer nobody has observed and nobody can reach. The fastest pulsar, the one at 716 rotations per second, has never been recorded glitching. Not once. It just spins. Steady, precise, silent. Nobody knows whether it will glitch. Nobody knows what the consequences would be for an object at that speed if the interior suddenly shifted. The models say it would be ugly. So far, the star has refused to prove them right. Earth has a weakening magnetic field and a growing dead zone over South America where satellites shut down just to pass through it. What is happening inside this planet is the next case this channel opens. Subscribe. The next file lands within days. 716 ticks per second. Still running. Still steady. For now.